So now let's talk about the output resistance of our Widlar current source. And so of course the importance of the output resistance is it helps us know how much our output collector current is going to change as our voltage across our collector emitter junction changes. And so of course, why would that voltage be changing? Well, that could be changing as our load condition changes. So ultimately we're saying, how does our output current change as our load changes? And so that's related to our output resistance. And so we can figure this out by using our small signal equivalent circuit. So just like I mentioned, we could have also used this approach for our Wilson circuit. We're not going to go through all the details of that, but you could try that by yourself, or you could look at the textbook. So our small signal equivalent circuits in the textbook, if you look on pages 701 to 703 in Neiman, you can see some more details about that. You do not need to know that, you're not responsible for that, but if you would like to look at that, you can see how this is arrived at. But if we go through that process, what we'll find out is our output resistance for our Widlar current source is approximately equal to R02 times the quantity 1 plus GM2 times the parallel combination of R pi 2 N and RE. Okay, and so let's close that. And so this is going to be our expression for our output resistance. Okay, and so let's define a few things. So we've actually defined these previously in our analog devices classes, but just as a refresher, so our R02, just like we've seen with previous configurations, this is just our small signal output resistance at the collector. So output resistance, in this case it's of our transistor Q2. Our GM2 is what we call the transconductance parameter. So transconductance parameter. And so as we had seen in a previous class, our GM in general is equal to ICQ over VT, where ICQ is our quiescent collector current and VT is our thermal voltage. Our R pi 2 is equal to, is what we call our diffusion resistance. And so if you recall our small signal equivalent circuit, this is basically the input resistance at our base emitter. And so as we had found in a previous class, our diffusion resistance is equal to beta VT divided by ICQ, where again our VT is thermal voltage, ICQ is our quiescent collector current. So what we see if we look at this equation for our overall output resistance of this configuration is that we have a vast improvement over our 2 transistor current source. So improvement compared to our 2 transistor source. And so that improvement is by a factor of roughly, so by a factor of everything in our parentheses. So that 1 plus GM2 times R pi 2 parallel with RE. And so we can see that here because we know for our 2 transistor current source, we just had the output, small signal output resistance of that transistor Q2. So what we could say is, well, sure, that's, maybe a big number. I don't know what are typical values for GM2, R pi 2, and RE. Well, so let's plug in some typical values. So if we look at some typical values as shown on page 702 of the Neiman textbook, what we see is this factor becomes, so we have 1, and then for the GM2, a typical value would maybe be 38.5 milliamps per volt, or we can write that as 10 to the minus 3 amps per volt. And then we have the parallel combination of our R pi 2, which is hundreds of k ohms, so let's say that's 217 k ohms. I'm just going to write that as 217,000 ohms in parallel with our RE. So like we saw in our previous example, our RE is on the order of single digit k ohms. So maybe this we can write as 9,580 ohms or 9.58 k ohms. So if we plug that in, we see that this is approximately 354. So our output resistance is improved by a factor of 354. So that's a pretty substantial improvement in our output resistance. And so of course, what is this output resistance really indicating? So to go back to what I said at the start of the video, we're talking about changes in our output current, or I out, with respect to changes in our collector voltage on our transistor Q2. And so we know in general that change is equal to 1 over our output resistance R naught. So as we increase that R naught, we're decreasing the amount that our output current is changing. So if you have any questions about our Widlar source or any of the other configurations or their output resistance, please don't hesitate to let me know.